boldly going where no science show has gone before. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with Diana O'Carroll. Hello, Diana.
Hello.
And also with me, Chris Smith. Coming up, diagnosing literary decay. Scientists have found a much faster way to sniff out old books that need urgent restoration, and that's to stop them falling apart. Also, we've got a new way to spot distant stars that could have planets orbiting around them, and it's all down to the magic chemical lithium. We'll find out how it works shortly. And how about this for a conundrum? What's green and losing 273 billion tonnes in weight every single year? I would say my mother-in-law, but I'm not that unkind. The answer is actually Greenland, and its weight loss is all down to melting ice, and we'll find out what the consequences of that might be in just a minute. Diana.
Yes, thanks, Chris. This week we're turning our telescopes on the heavens to discover how stars and planets form in the first place, and the processes that are modelling Mars today. And can they tell us anything about Earth too? That's all on the way.
Thanks, Diana. And sticking with the space theme, this week's Kitchen Science has got Ben and Dave discovering the origins of the solar system in a tub of microwaved margarine. So if you want to have a go at this week's experiment, all you need to do is grab a glass and some spread. They'll be along to tell you what to do with it very shortly. In the meantime, if you've got some questions for us, some comments or some feedback, then you can get in touch. Our email address is chris@thenakedscientist.com.
The Naked Scientists Podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
There's the old saying, never judge a book by its cover, and indeed you shouldn't. But now chemists are saying you should judge them by their smell instead. Publishing in the journal Analytical Chemistry, the authors have come up with a test that can measure how fast an old book is degrading, according to its odour. And this new sniff test could be really valuable to museums and document libraries because it has the potential to be completely non-invasive.
This is when books get old, they get musty, is that what you mean?
Yeah, you get these sort of funny smells. They might be like vanilla or grass-like, but I'm sure most of us will know them having walked into a library. But we actually did a question of the week about this a year and a half ago with one of the authors on the paper, and that was Jana Kolar, together with colleagues from the University College London and Slovenia, and they've isolated 15 main VOCs, and these are volatile organic compounds, which the paper releases. Now, each of these volatile organic compounds are emitted from the paper as a result of the original makeup of the paper in the document, the glues used to bind it, and the ink used for the print. So the researchers looked at 72 papers from the 19th and 20th centuries to find out which contained the most fragile components. And they already knew these included rosin, which is pine tar, and wood fibre, and they're related to increased levels of acid, like acetic acid, in the paper as it ages. And these acids can eat away at the paper itself, so they collected and analysed the volatile organic compounds using a combination of gas chromatography and mass spectrometry. And then, to test their own test, or find out which of these compounds were the ones that the library should be looking out for, they took a few small samples of the paper itself to look at its composition. So combining the results, they got these 15 VOCs, and they gave an indication as to the condition of the paper and how much acid or even peroxide, i.e. bleach, it's producing as it decays. And they've dubbed the smell test material degradomics. And now that they know that the smell test works on these 72 samples, they can develop this method to be completely non-invasive. And that's useful for any old documents library because currently you have to cut a small sample from a document in order to test how it's faring.
So that's ingenious. So you go to old books, you measure the smells that are coming off of them, you know roughly how degraded that book is, and so you can get a sort of smell fingerprint, which is an indicator of the level of decay, and that enables you to identify which books should be prioritised for treatment. But what can you do about a book that is in an advanced state of decay?
Well, it's usually all about moderating the atmosphere in which it's kept in, so humidity, how dry or not dry the air is. Sometimes you can apply chemical treatments, but most libraries don't have the money or resources to do that.
Because I thought Jana, who you mentioned in that, was developing some kind of spray or chemical that you could immerse the book in and it would neutralise some of those acids, and therefore it was sort of safer to keep it on the shelf for longer.
Yeah, that's interesting. That's a similar thing to the way the Mary Rose is preserved, actually, because the Mary Rose suffers from a similar problem of developing acids and various metals, and they have to spray that regularly.
Thank you, Dinah. So, as you say, never judge a book by its cover. Now, from libraries to way out into space, which is the question of lithium. Now, a scientific mystery, which goes back about 60 years, has been solved partially. I say partially, and you'll find out why in a second. Because when scientists began looking at distant stars, what they found was that there was something not quite right. If you look at what came out of the Big Bang when the universe was created, there were large amounts of hydrogen, the simplest element we know of, smaller amounts of helium, the next smallest element, and then traces of lithium, atomic number 3. Now, given that those things were made by the Big Bang, you should see roughly equivalent amounts of hydrogen, helium and lithium pretty much distributed all over the universe. So what people couldn't understand is when they looked at some stars, why was it that some of those stars had what we would call a normal amount of lithium, whereas other stars, equivalently old and of equivalent sizes, didn't seem to have any, or at least less than 1% of the amount that the other ones did. So where has that lithium gone? Well, a group of researchers in Europe, this is Garrick Israelian and his colleagues, have got a paper in the journal Nature this week where they think they've managed to solve this. What they did was a big survey, 500 stars, including Rod Stewart and Tina Turner. No, I'm just kidding. And they compared those stars, 70 of which had planets orbiting them, and they looked at the levels of lithium in them. And what they found, very interesting, when they arranged them in order of size and age and so on, so they were comparing like with like, those which had planets around them had no or very low levels of lithium visible in the starlight. But those that didn't have planets, so just solitary stars, had normal levels of lithium.
So were those ones battery-powered? No, why was that?
Well, a quote from the researchers themselves, they don't actually know. But what they say is it's now up to the theoreticians to figure out exactly how this happens. But they've got a theory. What they think is going on is that the presence of planets around the star in some way stirs up the surface of the star, and this pulls the lithium off the surface deeper into the star. And why that's significant is that the surface of the star, believe it or not, is not actually that hot. It's about 5,000 or 6,000 degrees, which is insufficiently hot to burn off lithium. But the interior of the star, which might be millions of degrees, 15 million plus degrees, in there it is hot enough. So if you get the lithium stirred up off the surface and going inside the star, it can then burn off. And planets, they think, perhaps in some way stir up the surface and make that happen.
Why is it useful to know this?
Well, apart from answering a very age-old mystery of planetary and cosmic science, what it also does is give us a clever way to find planets around distant stars, because up until now people have had to do painstaking and excruciating studies to look for distant stars wobbling a little bit or the light dipping a little bit as a planet goes between your telescope and the star you're looking at. This technique means that you can look at the light coming from the star, you can tell, because lithium has a certain signature written into that spectrum, whether there's lithium there or not, and if a star has no lithium, like our own sun, that's a good director that perhaps there are some planets orbiting it, so you should focus your attention there, not waste your time looking at stars that have loads of lithium, because they probably don't have any planets.
Great, so I won't be saying goodbye to my lithium batteries anymore. They're actually got a nice useful element in them. But anyway, I'm sure most of you out there will have run out of disk space on a computer at some point and had to overwrite a few files. And it looks like the short-term memory of animals isn't that far removed. Now, publishing in the journal Cell, neuroscientists reported that in mice and rats, newly formed neurons seem to be deleting older connections. And Kaoru Inakuchi and colleagues from the University of Toyama think that short-term memory is updated by new neurons emerging in the hippocampus area of the brain, which is sort of in the middle bottom bit. And these new neurons essentially overwrite the connections between the old ones. And the hippocampus is really special because it's one of the only places in the brain that we know can actually make new neurons. And the researchers looked at this by irradiating rats' brains, which considerably slows down the formation of new neurons in the hippocampus. And they placed rats in a chamber which would give their feet an electrical shock. Not very nice, but once the rats had this experience in their short-term memories, the researchers applied a bit of X-ray radiation to the hippocampus, and afterwards the rats continued to use the hippocampus to recall that fear memory. And in those rats without X-ray treatment, the fear memories were eventually displaced to elsewhere in the brain. Now, the researchers knew this memory displacement was occurring because they'd also looked at mice which were born without the ability to make new hippocampal neurons, and mice who received an infusion to block any neuron activity in the hippocampus experienced the same thing. So that way they could tell which animal was depending on its hippocampus for memory and which wasn't. And again, mice which couldn't produce new hippocampal neurons seemed to rely on their old short-term memories when they were placed in the shock chamber. And the researchers said that this is because there were no new neurons to displace the old ones and essentially push them into the long-term storage, which is somewhere else in the brain. So the conclusion is that if you can't make new neurons, then you could have problems because the brain's short-term memory is literally full. So perhaps this could lead to a better understanding of memory-related diseases like dementia and Alzheimer's.
It's very interesting because antidepressants also have the effect of increasing the survival of those new neurons being born in the hippocampus. And Perry Bartlett, who's a researcher in Australia, published some research a few years ago now showing that people, when they take Prozac, increase the proportion of those newborn cells that turn into neurons and also survive as neurons. And one of the symptoms of depression is poor memory. And one wonders, therefore, whether it's partly due to sleep disturbance and mood disturbance, but also because people don't keep enough of these nerve cells to erode those memories they want to displace or the memories they want to replace with fresh ones.
That's very interesting. I wonder if it's the same effect with marijuana as well.
Why do you say that?
Well, because marijuana has also been related to loss of short-term memory in people who are using it quite a lot.
You haven't had that experience?
No.
I'm just joking. Right, well, also in the news this week, we've got some worrying news emerging from Greenland because scientists have shown that the ice there is melting, and the time that it's doing that at, the rate at which it's melting at, is increasing. So the melt rate is accelerating. But how do we actually quantify how fast ice is melting from a landmass with any accuracy? Well, there's a paper in the journal Science this week. It's by Bristol University scientist Professor Jonathan Bamber and his colleagues, and it might be able to help us. And Jonathan's with us now to tell us a bit more. Hello, Jonathan.
Hi.
Welcome to The Naked Scientist. So tell us, first of all, what the issue is with Greenland.
So Greenland's the biggest ice mass in the Northern Hemisphere. It's got enough ice in it to, if it melted, you took away the whole ice sheet, it would raise global sea level by about 7 metres.
To put that into perspective then, we would be looking at the Pennines would be about the only bit of Britain left above water, wouldn't they?
No, it's not quite that bad, but you can say bye-bye to the Houses of Parliament, which might be a good thing, but, I couldn't comment on that. But 7 metres, that's about 25 feet, so I'm not suggesting that that's going to happen tomorrow or anything like that, but there is a huge potential for sea level rise in the Greenland ice sheet. I think the other thing about big ice masses like Greenland and Antarctica is that once you set them on a certain course, they're like the sort of super tankers of the climate world. Once you've pointed them in a certain direction, it's very, very difficult to turn them into another way.
How do you quantify how much weight, ice, water is going from Greenland? Well,
there's a variety of techniques, but what a lot of scientists have been very excited about in about the last 5-6 years is a satellite mission called GRACE, which stands for the Gravity Recovery and Climate Experiment. It doesn't matter what the acronym is, but it's an absolutely amazing mission. It's actually 2 satellites, and it's able to measure very, very accurately small changes in the gravity field of the Earth. And so if an ice sheet like Greenland loses mass or gains mass for that matter, it can actually measure those variations, and it does it on a roughly monthly timescale.
And what has this told you?
So a number of scientists have looked at this problem with GRACE and with other satellite data as well. And the problem has been with all the previously published results is that there's been a lot of variability in the numbers. In fact, the numbers have differed from each other by about a factor 2. Some have been double others. But what we've done is actually compared 2 different approaches using GRACE and an entirely independent approach for measuring the mass balance of the mass loss of the ice sheet. And they tie up pretty well, so it gives us a lot of confidence in our results, and we think that we've sorted out a lot of the issues that have existed with earlier observations. And I guess it's a pretty disturbing picture. In the early 90s, the ice sheet looked like it was relatively close to balance, maybe losing 50 gigatons of ice. A gigaton is 1 billion tons. And in the last few years, that rate has increased to something like 273 gigatons a year. And that's a lot of ice.
That's 273 gigatons, that's a cubic kilometre per gigaton. So that's 273 cubic kilometres.
So I mean, just to kind of try and... It's very hard with numbers that big to really know what you're talking about here, but 1 gigaton is about the volume of Lake Windermere, so we're talking about 273 Lake Windermeres.
Per year?
Per year. But I think the other interesting statistic I like is that 4 gigatons is enough water to supply the entire domestic water supply of the UK. So 273 is pretty much the water supply of the whole planet.
And that's just melting every year. Has that changed, though? Because one of the points you make in your paper is that there appears to be an acceleration going on. This would, one would presume, be secondary to global climate change. So what's the pattern of that acceleration?
We've seen... Grace only went up in 2002, and the reliable measurements are only about 6 years of observation. So we don't have a very long record from Grace. But just in that time, we have seen the rate of increase. We've seen it. I don't know. It's increased by about 2.5 times. So I think the mean for the period for 2003 to 2008 is about 180. But the last 2 years, it's gone up to something like 270 gigatons a year. So that's a big acceleration in mass loss. So
it's almost like Greenland's a sort of barometer of what's happening potentially in other bits of the world, isn't it?
Well, that's one of the interesting things, because I think until we started making some of these observations, most glaciologists and climate scientists felt that the ice sheets responded very, very slowly and not very dramatically to climate change. What we're seeing in Greenland is completely the converse, and I think it surprised a lot of scientists.
Thank you very much for joining us, and I wish that we could end on a happier note, but I guess I only can congratulate you on your research and not on the findings. Thank you very much, Jonathan.
OK, nice to talk to you.
That's Professor Jonathan Bamber, and he's a researcher at the University of Bristol. He's got a paper in the journal Science this week with his explanation as to exactly what's going on in Greenland with respect to loss of water because of melting ice.
Keeping you abreast of the world's best science, The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and Diana O'Carroll.
Thank you, Diana. This week we're looking at the processes that lead to the formation of stars and planets and how they actually form from massive great clouds of gas and dust, and also some of the surface processes that are modelling planets today, including Mars, and we'll get to that shortly. If you'd like to give us a call and ask us any questions, any comments for us, of course you can Twitter at us, at Naked Scientists, or the email address chris@thenakedscientist.com. We heard from Jordana Streeter, who is listening in Second Life. Don't forget, you can also get the programme beamed into Second Life. You go to the Scilands if you want to listen there. The question is, are we all parts of stars? Well, the answer is yes, basically. The Big Bang produced hydrogen, helium, and, as we mentioned earlier, a little bit of lithium. But most of the other elements, in fact, all the other elements, had to be made somewhere. And the answer is they were all made in stars. And stars used fusion to combine a nuclear synthesis and supernova explosions to combine small elements to make bigger and bigger elements. And so all of the elements that make your body today were made in the birth, growth and death of stars that lived billions of years before you did. Isn't that amazing? Diana?
Well, where do stars and planets come from? And here to answer that question is Professor Mark McCaughrean from the European Space Agency, where he's the head of research and scientific support. Hello, Mark.
Hello, Diana. How are you?
I'm very good, thanks. Well, let's start off now with some of the earliest models of planet formation. So how did humans really start to think about where the universe came from?
Well, I think, there's lots of models which we know from all of the religious textbooks and so on. So if we step ahead from those and look where we were in the 1700s, 1600s or so, and the important thing there is that this is after we realized and convinced ourselves that the sun was the middle of the solar system rather than the Earth. So once we get away from a geocentric model into heliocentric, things start to fall in place. There's a few important pieces of evidence that come into that. Firstly, all the planets go around the sun in the same direction in the sky. They all are more or less in circular orbits, and they're more or less all in one plane. And so immediately you might think that the solar system formed out of some kind of flattened disk around the sun. So we started with Descartes, Kant, and Laplace, well-known philosophers of the day, who figured out that if the sun and the planets around it formed in a flattened disk, they questioned how you would actually get a disk to form in the first place. So as Chris just pointed out a moment ago, we now know that planets and the stars that they go around form from giant clouds of gas and dust, and those clouds have to collapse. And as they collapse down, they're going to flatten because they're rotating very slightly at the beginning, these giant clouds, and through conservation of angular momentum, they're going to spin up on one axis more than another and end up being great big flattened rotating disks. And the philosophers knew that pretty well. So that's how we started off in the 1700s.
How did they get to that understanding? What kind of technology did they have at their disposal?
All they were really doing was applying, looking at observations of the sky with the naked eye and with the first telescopes. So Kant, for example, was well aware that the telescopes in the mid-1700s were able to start seeing faint fuzzy blobs out in space. And he thought those were perhaps dusty clouds which were beginning to form stars and the planets that go around them. So there was technology and use of telescopes. So it's mostly in terms of calculus and arithmetic. It was mostly theory work at that point.
And coming to our understanding in the 20th century, what do you think are the key sort of markers of our new modern understanding?
Well, what happened was very interesting. As though Kant and Laplace and later on Swedenborg and others put this model together, there became a major problem with it. And that is, if you look at the solar system which we live today, almost all of the mass of the solar system is in the sun. The planets have very little, less than 1%. But almost all of the angular momentum, the rotational angular momentum, is actually in the planets. And that was a real problem because the model they had been developing couldn't account for that. How did that evolve? So most of the mass was in the center, but most of the angular momentum outside. So there then was for 60 or 70 years, actually, until the early 1970s, major diversion into what we would call catastrophe theories of the formation of planets. So these catastrophe in the sense that nothing happened on its own. It happened in an event, a particular event, such as the passage of a massive star, a pre-existing star, past a nebula, which then pulled out through tidal forces, pulled out a lump of material from this forming star, and that was then able to collapse the planets. And there were lots of models like that, and they were very, very reputable for 60 or 70 years. But then it was observations that brought us back to where we are today, and that is in the mid-70s, 80s, and then the 90s, we actually began to see that stars around stars elsewhere in our universe were surrounded by disks of gas and dust. And that brought us all the way back to the Laplace model, which is today called the solar nebula model in today's parlance.
So it's kind of come full circle in a sort of century-like way. Can we actually see the stars and the planets forming? What does it look like in the telescopic images?
Well, when we look at the stars today, even the birth of stars is an interestingly modern phenomenon. It wasn't until the 1940s or so that we began to realize that stars had to be forming in our universe, and that we began to get evidence of that happening. There was an assumption before that many stars had just existed forever. They may have been born at one time, but the idea of star formation going on today is quite new. And so when we look at these places where stars are forming, and a very typical example is the Orion Nebula, which many people will be familiar with in the night sky as a fuzzy patch in the sword of Orion just below its belt. What we see there are giant clouds of gas and dust glowing, being heated up by the hot stars which have just been born in the middle, but we actually don't see much else at visible wavelengths, and that's because stars and planets are made out of gas and dust, and in particular the dust obscures our vision of the young stars. They're surrounded by this dust still, and you just can't see into those star-forming regions at visible wavelengths. However, if you look in the infrared or at much longer wavelengths, radio wavelengths, millimeter wavelengths, you can see a clear picture, and you can see these young stars slowly condensing, rotating at fairly high speed with disks of gas and dust around them, making planets.
But stars are quite bright and exciting, but what about the slightly duller things like moons and captured asteroids, that sort of thing?
Yeah, well, that's an interesting question. I mean, for example, how the satellites in our own solar system, how the things going around the planets occurred. In fact, there's a whole list of things. It may well be, for example, in the Jovian system around Jupiter and Saturn, that most of the big moons there formed the same way that the planets formed around the sun, through angular momentum being conserved and condensation in the disk to form those planets. But then you have the moon of our own moon, for example. How did that form? That's much bigger than any of the others as a ratio to the size of the planet that it's going around. And that may well have been a catastrophic event where a rather large object pre-existing in the solar nebula in the early stages, in the first tens, hundreds of millions of years, our solar nebula is probably full of planets which aren't there today, big lumps of material, some of which have fallen into the sun, some of which have collided with other planets. And that's what we think happened with the moon, is that something hit the Earth, the young Earth, there was no life, of course, there, and spun off a huge amount of material from the mantle, from the outer part of the Earth, and that then condensed into the moon. Other moons going around other planets, for example, Phobos and Deimos, the two main moons of Mars, are captured asteroids. They're very, very odd objects. They're not circular at all, and it seems as though they're close to the asteroid belt. They were just captured gravitationally.
Well, I guess they're harder to look at the further away they are in the solar system, but I'm afraid I'm going to have to cut you off there. We're running out of time, but thank you very much, Mark. That was Mark McCaughrean from the European Space Agency explaining the process that turns clouds of dust and gases into stars and planets.
In fact, we've heard a couple of people getting in touch with us about the issue of dust, because it seems that the word dust that we're using in the context of space seems a bit ill-defined for some people, because John in Colchester says, well, dust kind of implies that something big has been ground down to make the dust. And Nat Spirit, who's listening to us in Second Life, says, well, what actually do we mean by dust? Well, by dust, we're talking about small particles, because remember that when things form to start with, they don't necessarily have to form big things and then ground down into little things. Small things will attract other small things because they'll stick together one way or another. So when we're talking about dust, we're talking about amorphous material that can include big bits, small bits, and bits of gas. So it's a way of not having to define exactly what that entity is, but saying it's a mixture of chemical entities which have all of the necessary prerequisite ingredients to actually form planets and stars.
Lifting the lab coat on the world's best science. The Naked Scientists.
Still to come, we'll be looking into the processes that occur on the surfaces of planets, including how glaciers and sand dunes have sculpted the face of Mars. Don't forget, you can get in touch with any questions or comments. You can tweet at Naked Scientists, or you can send an email to chris@thenakedscientists.com.
Thank you, Diana. Now, comets with their iconic long tails are one of the most interesting things that we can see out in space from here on Earth, and including with the naked eye. Now, we already know quite a bit about comets from observing them with ground and space-based telescopes, and through the Giotto mission, which actually flew past Halley's Comet, if you remember, back in 1986. Well, the Rosetta mission actually sounds like perhaps something straight out of science fiction, but it's actually seeking to do something that no spacecraft has ever done before, or perhaps gone before, I suppose, and that's land on a comet. And this week it's done its final flyby past the Earth on a huge long slingshot, which will now send it off for a remarkable rendezvous. And Ben Valsler spoke to Professor Ian Wright, who's from the Open University, to find out a bit more about what we're hoping to learn from this exciting mission.
The Rosetta mission is a dual spacecraft mission which aims to send both an orbiter spacecraft and a lander spacecraft to rendezvous with and ultimately land on a cometary nucleus. Because of the distances involved and the speeds involved, it's not possible to just launch from Earth and hope to get there directly. One has to travel around the solar system a few times, building up speed by having gravitational encounters with planets like the Earth and Mars, and then getting flung out into sort of deeper space and ultimately getting fast enough so that one can catch the comet up.
It sounds like there's a lot that can go wrong. You're relying on this sort of slingshot effect around lots of different planets, and then you're catching something relatively small, a comet, millions of miles away. It
is quite daunting in a way. I think having been involved with a mission to Mars where you have something the size of a planet, and it's something you can actually see quite easily from your back garden when conditions are appropriate. Landing on a planet seems relatively straightforward. The comet is probably something like a kilometre or two across, and you've got a multi-billion kilometre journey to get there, and then you've got to find it and ultimately land on it. It is amazing, and of course, in that sense, I'm in the hands of the spacecraft flight engineers who are experts in this field.
And when did it actually launch?
It launched in 2004. It's already been travelling a few years already, of course, building up speed. It's now going off into a hibernation phase where it'll be effectively in deep space, ultimately hoping for a rendezvous and land towards the end of 2014.
And once it hits its target, once it lands on this comet and sets the orbiter around it, what are we hoping to learn?
The first thing that's quite interesting is, of course, one talks about an orbiter, but actually you cannot really orbit a comet. It's so small and it has no gravity. So one of the first challenges is really to understand how to fly with it. So the whole concept of orbiting is quite strange. In answer to the question, you can think of this as, as a human being, if you're on Earth and you were going to visit a new country that you'd never been to before, you'd have all kinds of questions that you'd want to know about the place. What's the weather going to be like? What's the temperature? What's the geography? What's the terrain? And in a human context, what are the people like? What's the food like? And all that kind of stuff. Actually, you can pose very similar questions in relation to the comet, although we don't expect any humans on the comet, obviously. But just simply any question you can think of about somewhere you've never been before. What does it look like? What colour is it? How cold is it? How active is it? Does it rotate? What's it made of? What's the surface like? Any of those questions, simple or fundamental questions, you can pose about the comet. And the Rosetta mission has been designed to try and get answers to as many of those questions as possible.
Most space missions are actually very specific. They're out there to look at certain areas of electromagnetic radiation or to look at very key things. It sounds like Rosetta is actually trying to be a bit of a jack of all trades.
I don't think Rosetta is particularly any different in a planetary exploration context. I think what a lot of planetary missions have is the widest diversity of instruments that they can possibly take. So, for instance, you want a camera, you want spectrometers, you want things that can detect magnetic fields. And once you get down onto the surface, you want to know what's the constitution like. Physically, what's it like? Is it hard? Is it soft? It's not simply a mission that's going to go to a comet and take a picture of it. It's a mission that goes to ask many different questions. The order of magnitude for the number of instruments is something like 20. I mean, there's like 10 on the orbiter and 10 on the lander, all different instruments designed for different purposes. It's quite possible that they won't all work. I mean, there's a certain amount of redundancy in this. So, one hopes the mission will be successful, whatever happens.
It's a very long way to travel if it turns out not to work. Is there anything that we can use it for on the way? Can we pick up bits of information about the environment it's travelling through?
Well, yes, it is interesting. And although I'd said previously it was about to go into hibernation, actually, it's got one more stop. It's going to fly past an asteroid. It'll be the second asteroid it's gone past during this phase. And yes, we use the opportunity at that point to turn some of the instruments on. Again, take photographs, look at magnetic fields and so on. Again, the mission was designed so that it would actually do this along the way, so that, yes, it spreads out some of the scientific interest along the mission itself. Because as you say, 10 years for a space journey is a long time, and it's a long time to get somewhere and find things don't work. So the mission has already done some science, and as I say, we'll continue to do some next year. Then hopefully next stop, the comet.
That was Professor Ian Wright talking to Ben Valsler about the Rosetta mission and how it aims to pick up as much information as it can from passing asteroids on its way to be the first spacecraft ever to land on a comet.
Laying the facts bare. I say. The Naked Scientists.
This is The Naked Scientists with Chris Smith and with Diana O'Carroll.
Yes, I've got a question here from Pamela, and she says, please could you help me understand why it is that we only ever see the face of the moon?
Well, one face of the moon, I presume she means. What's happening is that the moon actually is what's called tidally locked to the Earth. So the moon orbits the Earth. It takes about 28 days for the moon to make one complete circle. So if you imagine it starts at 12 o'clock and to go right the way around the clock face and get back to 12 o'clock takes the moon about 28 days. Of course, the Earth is turning inside that, taking 24 hours to complete a revolution, but the moon still takes a month to go all the way around the Earth. Now, the moon, as it goes round the Earth, is also turning, rotating, just like the Earth is, but very slowly. And it just so happens that it's turning at just the right rate, so as it goes around the Earth, it always turns so the same face is always pointing towards the Earth. So when you look at the moon's surface, you only ever see one face of the moon.
That seems very convenient somehow, doesn't it?
It does. You can demonstrate it if you don't believe me. If you get your fruit bowl, and I have an apple here, actually, which I'm yet to bite into. It looks very juicy and red. But if you have one piece of fruit and another piece of fruit, and if you make your apple go around your orange, you'll see that if it rotates at just the right rate, you can make it so that it will always have the same face pointing towards, say, your fist, which you're rotating it around, which could be the Earth.
Interesting.
Right, if you have any questions for us, of course, the email address for the programme, chris@thenakedscientist.com, and you can Twitter at us. It's @nakedscientist. So we've heard how stars and planets first form from clouds of gas and dust in the atmosphere, and there are lots of other different processes that go on once these planets are formed, though. And that means that weather and volcanic activity, meteorites coming in, the movement of ice or ocean swells, they all contribute to shaping the surfaces of planets. And it's often hard to work out exactly what's been happening when you try and wind the clock back. But one planet we do know quite a bit about is Mars, and Dr. Matt Baum is a researcher at the Open University, and he's actually been looking at the very changes that have helped to sculpt the Martian surface, and he's with us now. Hello, Matt.
Hi there, how are you doing?
Very well, thank you. So tell us a bit about your research on Mars.
Well, I look at surface processes on Mars, and these are generally, at the moment, things to do with either wind or water or ice. And I think Mars is a majorly interesting planet to look at because it has an atmosphere, it has ice, it has water or had water. And, so in many ways it's very like the Earth. And all the same processes, all the same physics happens on Mars as happens on the Earth. And it's also got a little extra added piquancy, which is there may or may not have been life on Mars at some point. So that's why we aim to look at these processes. It's all really tied into the search for habitats and the search for evidence, possibly, of life on Mars.
It's interesting you mentioned the sort of biological role of shaping the surface of Mars, because we had an email from Blaine who says, were the red sands of Mars caused by biological activities? Because when the levels of oxygen rose on Earth billions of years ago, large quantities of iron rusted out of the atmosphere, and that left iron oxide deposits in rock. So could the same thing have happened on Mars, he asks?
Well, possibly. I think it's probably not the correct reason. I think the reason sands on Mars are red is really just due to a magnetite composition or a ferrous iron mineral composition. Mars may or may not have had an ocean. If it did have an ocean, it probably didn't exist for a very long period of time, relatively speaking, not like the Earth's, which has been around for billions of years. So, we're loath to rule anything out until we actually go there. I mean, that's one of the wonders of planetary science. There's an alternative answer to almost everything. So
people have found quite good evidence for a lot of water on Mars in the past, and correct me if I'm wrong, an ancient tide line, a sort of an edge of where that ocean would have been, but I think the ocean being long gone, that tide line has been reshaped by other geological processes. So it's all higgledy-piggledy, but is there nonetheless?
Well, it's controversial. There are quite a few groups of scientists who think that when you actually look at the more recent data that we have from Mars, which have a much higher resolution in terms of, how many meters each pixel in the image actually represents on the ground, they haven't found any good evidence for these shorelines. So the shorelines, are still heavily under debate. And, again, Mars planetary science as a whole, it's a science in flux. There's a lot we don't know, and as each hypothesis gets built and then torn down again, eventually we get closer and closer to the truth. That's, I guess, why it's so exciting.
So what are you actually looking at directly yourself?
At the moment, I'm doing an awful lot of work on what are called periglacial terrains, and they're terrains that have a lot of ice in the surface, but also some degree of thaw. And if you've ever been to, let's think, Siberia or northern Canada, you might have seen these amazing patterned ground, sorted stone circles and stripes, and they almost look like human beings have made them, but actually they're a class of self-organising landform, which means that as you have a cycle of freeze and thaw, rocks get moved by frost heave, so ice is a different density to water, so you get differential movement of rocks, and it actually sorts them into amazing circles and patterns. And we have been seeing very similar sort of things on Mars, and obviously this is quite controversial and quite interesting because you can only get this if you have some element of thaw of ice. So up until this point, a lot of people have said, well, we know there's ice on Mars and we know there was water years ago, but we don't think there's actually been any melting of the ice, or not significantly, for maybe hundreds of millions of years. But what we're looking at are sorted stone circles and sorted stripes and all sorts of other periglacial landforms that look just like the sort of landforms you see in Siberia or Alaska or Canada. So the conclusion is there's been some thaw in the very recent past on Mars.
And what are the implications of that, Matt?
Well, I think the implications of that are that the climate was perhaps warmer than we previously had thought, just in the last few million years, or that maybe there's some other unknown process that allows this ice to thaw. So maybe there's an awful lot of salts dissolved in it, and as anyone who's thrown salt onto the drive to help clear the ice knows, if you have ice, salt in your water, that depresses the freezing point. So, and all these things are interesting because they hint at a possibility of a more habitable Mars than we previously thought.
Which, of course, might have implications for not so much life once, but the existence, perhaps, of life today.
Well, yeah, I have to say I'm generally a bit of a non-believer in terms of life on Mars. I tend to think that if life ever got going, it would be so obvious that we'd be able to see it, from Earth and from, very easily. But, it does imply that if Mars was more recently wetter than we thought, has a much higher chance of there being current life or dormant life. Maybe if it was 1 million years ago, there was habitability. Obviously, even if that stopped 500,000 years ago and everything that was alive there is now dormant, we wouldn't be able to see it unless we actually got in there with a shovel and started digging. So,
what can we learn by studying these sorts of things on Mars about other planets, maybe not even in this solar system?
Well, I mean, Mars is a counterexample to the Earth. Everything we know really about geology and planetary geoscience in general, we know from the Earth. Studying Mars gives a counterpoint sort of ideas about how planets evolve. In terms of outside the solar system, I mean, it can give us hints about the sort of things we might be seeing, but of course it's going to be impossible for us to ever, or I say ever, but in our lifetimes, ever have our hypotheses tested. You may think, perhaps this exoplanet has sand dunes or glaciers or rivers, but we'll never know, at least not in our lifetime.
Then science fiction's safe for a while. Thank you very much, Matt. That was Dr. Matt Baum, who's from the Open University. He's looking into the processes that are sculpting the surface of Mars.
And now it's time for Kitchen Science. And this week, Ben Valsler and Dave Ansell are raiding the fridge, that's a change, to find out how margarine and meteorites can tell us about how planets form.
For this week's Kitchen Science, we've been back into the fridge to find another one of those things you've got at home that can show you something amazing about the world. A few weeks ago, Dave used some lard to show us how mountains form and how there's around 6 times as much rock under the surface as there is sticking up above it. And this week, he's going to show us something else, but this time he's using margarine. So Dave, what are we doing?
Well, basically what we want to do is melt some margarine and then leave it to stand.
Well, when we did the lard experiment, we melted it with a cup of boiling water, so are we doing that again?
It doesn't seem to melt very well with boiling water. There's no reason why you shouldn't do it. It doesn't matter how you melt it. I'm going to use a microwave.
How much do we need to melt?
Doesn't really matter. Basically, you want to get as small a glass as you've got and at least try and half fill that glass.
OK, and you've brought a shot glass with you as well, so this really is barely a tablespoon of margarine.
Yeah, that's basically it. So I'll get some and put it in the glass.
Now, in particular, you have a block of margarine, the type that's supposed to be used for baking. Could you use butter instead, or olive oil-based spread?
I think any spread will work, but the very cheap, simple margarines will be a lot more obvious than the more expensive butters.
So your supermarket shopping on a budget is really paying off?
It's a good excuse, anyway.
OK, so we have our cup half full of margarine, and now we'll put it into the microwave. How long should it take to melt?
Not very long at all. In fact, fats are very good at absorbing microwaves. So I've put a plate underneath the glass because it has a tendency to boil over if you're not very careful.
OK, so as always, if you're dealing with microwaves or any kind of cooking, things can get very hot, so do be very careful. Let's put this in.
So I'm only going to put this on for 10 seconds on a low setting. If it hasn't quite melted, I'll put it on for a bit more.
So that's had its time. Does it look ready?
I think it's just about molten now. I'll take it out. And very carefully, I'll just lift this out.
It does almost look like a glass of orange juice now, and it's ever so slightly steamy. So again, do please be careful if you're doing this at home. So we have our glass. It smells very strongly of margarine around here, but we have our glass of molten margarine. What's next?
Now you want to wait a minute or two and just see what happens to it.
What are you expecting?
The way you make margarine is you take a fat, you melt it, you then mix it up with a liquid, water will do, and you mix it up with a surfactant to act a bit like washing up liquid to make the two mix together, and you end up with something a bit like salad dressing. Then you batter it lots more and squirt it through lots of very small holes, and you get salad dressing with incredibly tiny lumps of fat and lumps of water, and it's actually stable.
So margarine really is an emulsion of vegetable fat and water and probably a few other things. I imagine there's some salt in there. But what good is that to us now?
Well, now when you've heated it up, you melt everything. That means it can change shape and you lose all that stability. So the two separate out. And if you have a look at it now...
It's just been sat on the side for a while, and actually down at the bottom of the glass, it's gone crystal clear. The rest of it still looks like orange squash. But is that water collecting at the bottom of the glass?
It'll be water and whatever else they've put in there, I don't know exactly. But yeah, it's basically just water collecting at the glass and the fat floating up on top of it.
By melting an emulsion like margarine, you can cause it to separate out into its component fat and water. But what's that got to do with anything important?
This is actually quite a good model for one aspect of how planets form and large asteroids. All the rocky parts of the solar system were formed out of the random rocky stuff, the silicates, which are floating around in the protoplanetary disk as the solar system was forming. And some of that is still preserved in some of the meteorites which land on Earth. These are called chondrites. They're actually made of little tiny spheres of molten stuff which are melted by the young sun and they've kind of stuck together to form meteorites.
So we can have a look at these when they land on Earth and it tells us something about the young solar system.
Yeah, it basically tells you what the original stuff which made up all the rocky planets of the solar system was.
And what's that got to do with margarine?
Now, when these kind of clump together and form bigger and bigger lumps, they started to melt. And also they got to a big enough lump that it had its own gravity. That meant that the heavier things tended to sink not to the bottom, but into the middle, the centre of the planets or the protoplanets. And the lighter stuff floated to the top, just like our margarine.
So the water's sinking in our liquid margarine because it's more dense, it's pulled down by gravity. The same thing happens in large asteroids when they get hot enough to be liquid. But how do we know this happens?
Well, some of those original large asteroids got bashed into by other large asteroids and got broken apart, which means you find other types of meteorite. Some of them are stony, sort of basalty type things, a bit like the stuff you'd find coming out of volcanoes mid-ocean. These are equivalent to the stuff which has floated up to the surface, the sort of mantles and crusts of asteroids.
The fat on our margarine.
That's right. And others are kind of basically made out of iron and nickel, very, very heavy, very dense metals. And these are the cores of the asteroids which got blown apart. And these are quite rare, although they're much more easy to find because you don't find anything else like them on the surface of the Earth. So these are like the water from our margarine.
So because we find bits of asteroid that are either one thing, the light stuff, or another, the heavy stuff, we know that at some point they must have come together and gone through exactly the same process as this margarine and separated out. Does the same thing happen in the Earth? I know we have a core of iron.
Yeah, it's basically exactly the same thing. The Earth is actually a lot bigger than an asteroid, as is probably obvious. And so you actually tend to get even more layers. So you'll get sort of the core, inner core, outer core, various layers inside the mantle, and then a crust on the surface, which is even less dense than the mantle. So because there's more gravity there and it's been hot for longer, it's had more time to sort of fractionate out to form more layers.
So once again, the cheapest stuff Dave's got in his fridge shows us something important about our own planet. That's all we have for Kitchen Science this week. We'll be back with more very soon.
So, melted margarine forms layers just like protoplanets and hot meteorites, with the denser materials being pulled towards the middle by gravity. We'll put pictures and video on the website at thenakedscientist.com/kitchen science.
Sounds like some kind of exciting food you could eat, doesn't it, that description?
It sounds disgusting.
You can go to sort of cross between McDonald's and Starbucks, I suppose.
Ugh.
Sorry.
Bringing the facts to bear. The Naked Scientists.
Right, I have an email here from NASA. Now, that's not the American Space Agency, but it's actually a person called NASA. And he says, where do comets get their water from? So, Mark, do you have an answer?
Yes, I think one of the things you have to realise is that when the solar system was very young, it was very much hotter. And so you had a lot of water in the solar system, but out to about Jupiter, it was pretty much evaporated off or incorporated into the places like the Earth. But the comets are great big lumps of icy dust and muck still left over from the early part of the formation of the solar system. It's just leftover stuff.
Right, OK, I've got another question here from you from Joe DeLuco. And he says, what is it that keeps planets spinning as well as keeping them moving in their orbits?
Oh, well, one of those is both fairly simple pieces of physics. One of the things keeping them moving in their orbit, there's nothing to stop them. I mean, they're not hitting anything, so to speak, so they're not losing any energy, and they're not losing, more importantly, angular momentum. So angular momentum is a conserved thing. It can't just be taken away by just by wishing it away. It has to be taken away by things, and the Earth is just sitting there rotating. Nothing's taking its angular momentum away except the Moon. The Moon is actually going to steal some of the Earth's angular momentum, slow it down, and at some point in the future, the Earth and the Moon will be locked together. They both have lost angular momentum at the moment. We only see one face of the Moon, and in the future, only one face of the Earth will be facing the Moon. So you'll only be able to see the Moon from one side of the Earth and vice versa.
I think somebody wrote a pop song about that was very popular.
The problem is it takes billions and billions of years, and we'll see if those CDs still play them.
Yeah. Right, I've got another question here for Chris. And it's from another Chris in Lowestoft, and he says, why is it that stars appear spiky and not spherical, and why do they twinkle?
Well, stars are spiky. They're a seething mass of hot material. So from the surface of a star, if you got close, you would see these big tendrils of material going up to form this seething mass of material which it spikes off the surface of the star. But the reason they're actually twinkly when we look at them is nothing to do with that. They're twinkly when we see them through the Earth's atmosphere, because the Earth's atmosphere is not uniform. There's air which is at hotter temperatures and therefore less dense, and there's air which is at colder temperatures and therefore more dense. And when light goes from a medium which is more dense into a medium which is less dense, it changes speed. In fact, it speeds up a bit. And it's that change in speed that causes the light to bend a little bit. And that means that when you see rays of light coming from a long way away, they appear to be coming from one place and then another place, another place, and then another place, because the light ray is being bent alternately as it goes in and out of warm and cold patches of the Earth's atmosphere, and that's what makes the star twinkle. And you see the same thing happening if you look at the lights from a harbour across a sea harbour or a port, for example.
And you can also get polarised filters even to put on your camera, and they will make the stars sort of pointy in numerous different directions as well.
Indeed.
I've got another email here from Andrew and David McCluskey, and they say, why is it that electric kettles make noise when they're heating up?
Well, I have to be very quick with this one. The answer is because the element puts so much energy into the water expands around the element to a point where it wants to boil. It forms a bubble of water gas, steam, and that bubble, as it rises through the water, then gets cool. It collapses in on itself and does what's called cavitating and goes bang or pop. It's a sort of reverse pop, and that's the noise you can hear.
Right, well, now it's time for Question of the Week, and this week's question has a distinctly weather-like flavour, following our weekend of gales.
This is Jade Forrester from Leamington Spa. I've always wondered about the old saying, red sky at night, shepherd's delight, red sky in the morning, shepherd's warning. Why do we get red sky, and how does this saying predict the weather for the next day? Thanks, you guys!
And there have been some spectacular sunsets this week, but what do they all mean?
My name is John Hammond, forecaster at the Met Office. Well, we get red skies, and of course here in East Anglia the skies are pretty impressive because the lack of hills or mountains mean we see so much of them as well. But we principally get these red skies because of how light is reflected and bounces around basically in the atmosphere. Now, we get them mostly, of course, first thing in the morning or last thing in the evening. It's basically because the sun is so low, all the other elements of the spectrum, if you like, right the way down towards those blues and indigos, are being bounced around the atmosphere, leaving behind those that are the oranges and the reds. You need, of course, the angle of the sun to shine from underneath the cloud up towards the base so you can see it from the ground. But when you've got higher cloud, then you've got more chance to do that. Now, when you get higher clouds, what often can be the case is that you've got clouds called cirrus clouds, or cirrus stratus, or autocumulus clouds, which are fairly high in the atmosphere. So they're anything sort of from, say, for example, 10,000 feet right up towards 30,000 feet. Now, these clouds themselves can be the forerunner to a weather system coming in off the Atlantic Ocean. And then overnight, of course, that cloud lowers as this weather system moves in from the Atlantic Ocean and brings us a spell of rain, or even perhaps snow during the winter, of course, as well. And, of course, you get the converse effect during the course of the morning, when you have red sky in the morning, shepherd's warning, which I suppose is not very good news if you've got sheep and you want them to keep dry during the day, because, of course, that means red sky in the morning, the cloud's going to lower, so you'll be getting rain, but during daylight hours rather than darkness.
So when you have higher cloud coupled with the sun at a low angle, you are much more likely to get red skies, and that high cloud can often be indicative of impending rain. So if you get red sky in the evening, the rain might come during the night and leave you with a dry sunny day afterwards, whereas red sky in the morning means rain during the day.
Now, we had some discussion about this on our forum, about the direction that this takes, and Giza said, because if you have the sun setting in the west, the only way the light can hit the clouds above an observer is if there aren't any clouds far off in the west to obscure the sun. Because the weather in the UK comes to us from the west, it could be an indicator of clear skies coming our way. So a rising sun in the east will pick out red clouds if they were moving in.
And our meteorologist actually said that this red sky prediction can be used just about anywhere in the world. So it's not always true, but you can get it to work with some high clouds and low sun. Well, next week's question is also about reds.
Hello, I'm Karina from Quito, Ecuador. And my question is, why white wine is served chilled and red wine is served at room temperature?
What would happen if you served a cold red wine and a lukewarm white? I think we need to test this one on someone who doesn't drink wine, maybe. Help us to answer this question by email, chris@thenakedscientist.com, or write on the forum, and our special website for discussion, and that's thenakedscientist.com/forum.
It's actually highly appropriate that you mentioned that, Diana, because next week I'm actually off to Adelaide in Australia, and that's actually one of the world's top winemaking regions. So I'll be meeting some scientists who are actually studying what makes the best grapes for winemaking, and also how to stop bushfires from spoiling a fine vintage. I'll also be taking a tour of a brand new facility that's going to study how plants grow, and this is amazing. They all get moved around on conveyor belts and studied by lasers and things. So if you want to find out how that happens and how it works, join me next week as I pay a visit to some of Adelaide's top scientists. Now, meanwhile, something else very important is that The Naked Scientist has been selected as a finalist in this year's Podcast Awards. We've been here 4 times now, so if you want to see if you can help us to win this time, then do please, if you like what we do, give us a vote. You go to podcastawards.com, and if you scroll down to the bottom of the screen, down on the bottom left, and put a tick in the Naked Scientist box, and then validate your vote with an email, then with a bit of luck, maybe this time we'll actually get through. Production this week was by Ben Valsler, Dave Ansell and Diana O'Carroll, and I'm Chris Smith. Until next time, thank you for listening, and goodbye!
The Naked Scientist podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC and UK FAST. For more information, look us up online at nakedscientist.com.